Okay, I wanted to make sure I wasn't misspeaking. So let's take a look at it. So we're on problem 9 or question 9. No, question 8. Sorry, question 8. 250. So now that 250 newtons, that's going to equal, since the velocity is constant, there is no acceleration. So therefore, the this is this is the deal. So for this one, since velocity is constant, acceleration equals zero. So acceleration equals zero. So what that means is, fancy physics writing, the sum of the forces in the x direction are equal to zero because there's no acceleration, because ma is equal to zero. Okay, so that would mean you got a positive 250 Newton force going this way, and then opposing that force is, and then the kinetic friction is going this way. So kinetic friction is equal to 250 newtons, and or the force of the kinetic friction is 250 newtons, and therefore, but we also know that F of k is equal to mu of k, which is what we're trying to find, times that normal force that we found earlier. Okay, so this is the deal. All right, solve that one. You might be going, oh my God, yeah, there's 40 of these, so this might take a minute. No, it won't, because watch. We'll fly through this. Okay, I forgot we didn't even talk about this. All right, move on. Okay, wax, that is low friction applied to the ends of skis. Oh, or has a high amount of friction applied along the central region. I think that's true. I forgot to talk to you about the skis. Okay, what are the forces at play while surfing? All these. We didn't have really too much of a chance to talk about those, but the buoyant force, gravity, drag, all of that is going on when you can watch that PhD physics thing, but all that stuff is going on. I talked earlier about why do dragsters burn rubber. All right, now I want you to watch that Smarter Every Day on curling, and also take a moment to watch the curling rocks video, because it's hysterical. All right, it's fun. All right, so so here's one. Here's force of kinetic friction on the stone. There you go. If the kinetic friction between the ice is 0.168, what is the force of kinetic friction the ice puts on the stone? Again, F of k equals mu of k times the normal force. 19 times 9.8, right? Okay, so you got this. If the stone were released, oh, okay, here we go. This is cool. If the stone were released from, I want to do problem 16, then we'll, I got these out of order a little bit. So 15 and 16, whatever. We'll fix it. I mean, we won't fix it. You're smart enough to figure out that, 16 should be underneath 14, but that's okay. So curling, we've done this before. On problem 16, let's take a look at 16 real quick. Here's what's going on in problem 16. Here's what's happening on problem 16. You've got curling stone, has a mass 19 kilograms. Its initial velocity is 7 meters per second. Okay. All right. And you computed in problem 14, you computed F of k. Okay. Now, how much work is F of k going to do on this thing? All right. How far is this thing going to go? All right. So here's what we do. Well, we know that F of k, the force times the distance, is equal to the change in kinetic energy. All right. And the change in kinetic energy is F final is equal to 0. So we've got 1/2 m times 0 squared minus 7 squared, like that, where m is equal to the 19 kilograms. And you figured F of k from problem 14 times the distance, and F of k is the negative force that's working against it. But look what happens. This is going to be a minus 1/2 m 7 squared. It's negative because that minus sign is factored out here. So those minus signs go away. So you get f of kd is equal to 1/2 m times 7 squared, where the mass again is 19. And you got to solve for d. I think you can do that. Get this number, divide by f of k. All right, I'm going to stop here and we'll look at the next part.